So in this video we're going to take a look at measuring refractive index of glass using a parallax method. So we've got a straight line on our piece of paper, we've got a transparent block laid over the top of it, and we're going to adjust the pin height until the pin and the image of the line both move together, they don't separate. So let's have a look at that in a bit more detail. So this is what it looks like if we're looking down from above. So we've got the line drawn on our paper, we've got the pin touching the glass, we've got them lined up so they're in a straight line, and we're going to move up and down according to this diagram, but we're really going to move horizontally, and you can see we've got the glass block. So these are going to be our two setups. So we're going to do two separate measurements, but they should both give us the same value for refractive index. Okay, so first of all, what are we going to see? So if we've got the pin height wrong, then what we're going to see is when we move position, the line and the pin are going to move by different amounts. So here we've actually got the pin too high because we can see the image of the line moves more than the pin does. So our pin is currently too high if you're looking at this. So the question is, why are we getting this movement? What is going on? So I'm going to look a little bit at refraction to start off with. So you should know that if you put something in water, it looks like it's bent. And this is all to do with the formation of a virtual image from the refraction of the light. So what happens is when we're looking at something in water, it will look to us like it's higher than it actually is. And you can see on the diagram where the image is formed, and that's why it looks bent. So if we can get the pin at the right height, or the same height as the image, those two should experience the same parallax or same movement when we change our position. That's why they move together when we get exactly the right pin height. Okay, so this is us now looking side on at the block. So we can see we've now got the pin at the same height as the image of the line there. So this is where we've got what we want. So I'm going to draw two rays passing from the same point on the actual line, and I'm going to use the one right on the corner. And the reason we use the one on the corner is that forms the extreme of the image as well, and that will also be on the boundary. Okay, so that's where our virtual image forms. So to cut out some of the unnecessary information, I've chopped out some of the rays and we've just left with this one. And the key is going to be that these two distances are the same. So let's label some angles on here. So the angle of refraction is going to be the same as the virtual angle of incidence. Remember, our eyes or our brain thinks light travels straight on. The actual angle of incidence is going to be slightly smaller than that. And we can use the tan function, because we've got two right-angled triangles, to get expressions for the tan of each of those angles. And this is where the fact that they both have a W in them is useful, because when we do tan of the angle of refraction divided by the tan of the angle of incidence, we get this h over h minus x. Okay, so why is that important? Well, I'm going to now use Snell's law, and we know that the second material is air, N2 is 1, so we get this expression for N1 is sine theta V over sine theta A. Now what you won't know is that for small angles, tan theta and sine theta actually give pretty much the same value. So as long as our angles are small, we're going to get the angle of refraction is calculated by doing h over h minus x, which is why you will have quite a narrow block in order to do this, to make sure that the angles are in fact small. Okay, so after that diversion, let's now get back to the actual practical. So when I've made my adjustment, I reckon that the height above the ground for the parallax to be the same is 31.8 centimeters, and I should be giving this to the nearest millimeter because I'm using a ruler with a resolution of 1 millimeter. So it doesn't matter which distance unit I use, it should be to the nearest millimeter. Okay, so then the height of the block when it's got sort of the longest side as the height, I got is 95.3, and that gives me a refractive index of 1.5, which makes a lot of sense because I've used these blocks before. I know they're 1.5. Okay, so then we can repeat this after we've rotated the block. So having made an adjustment, I now get a new hex and I've got a new H. And from that we get a new refractive index, and we can see exactly as expected we've got something very similar, about 1.5. So now we've got two measurements of the same thing, so we can calculate an average. Well, mine's just going to be the same. So we've got the average refractive index of the glass is 1.50. All of these numbers are 3 significant figures because all of the data that's gone into the calculations is 3 significant figures. To obtain a reliable value for the vertical distance between the paper and the pin, it is important the pin is horizontal. Explain briefly with the aid of a diagram how you checked that the pin was horizontal. So the way I do this is I take 2 measurements between the pin and the desk at each end of the pin, and we should get the same value if it is in fact horizontal. Okay, so moving on to an electricity experiment. Starting off with a parallel circuit. So we're measuring the EMF of our power source and the current through lamp 1 to start with. So we're going to measure the potential difference and the current in lamp 1 and lamp 2 in this parallel circuit. So we've got our table, so let's first of all put our units in our column headings. It should be no surprise we've ended up with the same potential difference. They're in parallel, so that's what we expect. And we've got pretty similar currents. Mine actually slightly fluctuated, but those two are pretty close. And that makes sense because they're identical bulbs. And then using R equals V over I, we can calculate the 2 resistances that we've got there, which I'm going to give to 2 significant figures because the 0.18 and 0.17 are 2 significant figures. Add together the 2 values. Okay, there we go, 25 ohms. Complete the column headings, we've already done that. Rearrange the circuit so they're now in series, but the voltmeters are in the same place. So I've got pretty much the same voltmeter reading. It's slightly increased, but we've got pretty much the same, which shouldn't be a surprise. We're using the same power supply. Well, the current now, exactly as you'd expect, is much smaller because we've now got 2 lamps in series, so we get a smaller current. And now if we want to calculate the combined resistance, we've got V over I, you can see it's now 32 ohms. A student suggests the values of RS and R2T should be equal. State whether your results support the suggestion and justify your statement with reference to the calculated values. Okay, so no, they don't agree. How do I know that? Well, the difference between them is 7 ohms. So one was 32, one was 25. But that is going to be well beyond any experimental we have. So there has been a change in resistance, so they don't agree. So how did I know it was beyond experimental error? Well, just a side note here. We worked out what the resistance of each of the resistances was separately. Now we know them all to 2 significant figures. So the resistance of the first resistor is 12 plus or minus half an ohm, because any number between 12.5 and 11.5 rounds to 12. Same thing with R2, plus or minus half an ohm. So when we add those together, we get 25 plus or minus 1. So that means the resistance of those two added together is anywhere between 26 and 24. For the second experiment, we're going to get, it's 32 plus or minus a half, so it's anywhere between 32.5 and 31.5. So those 2 ranges do not overlap, so the experiment shows that the 2 values are not equal, and that's what I'm really commenting on when I say it's well beyond experimental error. State without reference to the values of resistance that you've calculated one piece of evidence that have observed during the experiment that shows the temperature of the filament changes. Well, that's the brightness. So the brighter a bulb is, that tells you the hotter it is. So in the second experiment, my bulb was dimmer, which tells you it is in fact cooler, and that finishes off this experiment.